So this is session 3 of the video interview with Dana Scott. Dana is in Berkeley, California, and I'm in Edinburgh, Scotland, and it's January the 12th, 2021. Dana, when you were at Berkeley during this period, Rabin was also there, and you took the chance to work with him again, this time, I believe, in arithmetic. You also invented famous notion of Scott sets in connection with non-standard models of piano arithmetic. So there's a very interesting story there. Could you tell us, please, about your interaction with Rabin and the work on arithmetic?
Rabin and his wife came to Berkeley for a one-year sabbatical. It turned out to be the only other time that I ever had a chance to work with him, because he was then, after that, went to Jerusalem and then to Harvard and back and forth, and we were never close together again, unfortunately. We had very, very good time working together there. He discovered a new proof of Trachtenbrot's theorem that the set of first-order sentences true in finite structures is not axiomatizable, not enumerable, and we've had some other results together. But alas, that was my last working with him. I do want to tell a story about him and his wife, Ruthie, however. In those months, she was pregnant with their first daughter, and they went to a doctor in Berkeley, and the doctor said, I would like to take some x-rays. And they said, oh no, we don't want any x-rays. X-rays can cause mutations. The doctor said, well, you know, some mutations are good. It didn't convince them. And that baby turned out to be Tal, who has had a fantastic career of her own, fortunately without any additional mutations. So that's one of my memories about the Rabins. There was quite a lot of activity there, many visitors coming and going in Berkeley. That was also the time that I worked with John Myhill. He was still at Stanford at that time, and he had come to give a talk about using definability with ordinal numbers in set theory. And after I thought about it, I realized that ordinal definability is a very widespread notion. And so he and I got together to write the paper about ordinal definability, which in particular shows that with using those sets that are hereditarily ordinal definable, that is, not only the set, but all their elements and elements of elements, elements are ordinal definable. Those sets form a model for set theory that satisfies the axiom of choice. So we are very pleased with that. And it's not surprising that Gödel said, oh, I thought of that years ago, but my proof with the constructible sets was so much more important to get to the continuum hypothesis, I never told anyone about it. Oh, well, that's what happens. I can't remember all the details right at this moment, but I also thought about non-standard models. Abraham Robinson was making great strides in non-standard analysis, and so I had some small results along that line. That was another interest.
So in a different direction, you mentioned once to me that you were party to early conversations about starting a CS department at Berkeley. So can you tell us about those conversations or those interactions?
Yes, well, of course, Harry Husky had been at Berkeley for some time and had many students here, but he was more concerned with engineering aspects of computers. Everything was done in the electrical engineering department. But in 1957, a Belgian computer man had come to Berkeley, René de Vogelaar. He was very, very enthusiastic proselytizer and was particularly very strong about algol and the use of algol, and that how algol should really change programming. And so he introduced me to algol, and there was quite a lot of activities, seminars, and things like that, trying to understand what might be the opening up of design of computer languages. So the question came up because in other places too, there was an interest in having more concentration on study of use of computers, to have a separate computer science department in Berkeley. Also, Zade was here, and he was very instrumental in trying to develop a new departmental structure. And so I was involved in early discussions on that, which didn't quite gel at the time. However, because I left Berkeley only after 3-4 years here, they then established the EECS department quite soon after that. So that was in the middle 60s when that happened. And of course, it's become a very major department in computer science. But I'm afraid I didn't have much to contribute to the development of that department, even though I was involved in discussions about it at the time.
So the EE department was there initially, and then that became the ECS department. Is that what happened?
Well, there are really two departments.
Ah.
And somehow, I mean, computer science is a sister department to the pure electrical engineering department. So I think there's still two separate departments.
Ah, okay. Well, as you said, you didn't stay. In fact, you moved so much longer. You moved from Berkeley to Stanford. So how did that move occur? So 1963, I think.
Well, John Myhill, who had been at Stanford, decided to leave Stanford. This was after we had done our joint work together. And so there was an opening at Stanford, and Kreisel was much involved in Stanford. He came several months every year. He went back and forth between America and Europe. And I was still very, very close to Kreisel at that time. And so he suggested that I come move over to Stanford. There had been some unhappiness at Berkeley because with a number of new appointments, the mathematics department was branching out and had many major appointments in various branches of mathematics. And there was a certain amount of animosity toward Tarski and logic because Tarski had pushed the development of logic so much. And so there were some rather hard feelings against Tarski at that time. And so whether it was a foolish move or not, I decided to get away from that. And so when Kreisel and Supes at Stanford, Supes, of course, had been a major professor there for some time, when they suggested that I move from Berkeley to Stanford, I decided to do that. I had some students working under me at Berkeley. I'm not sure that all of them were ready to finish, though, but I finished them up remotely after I moved to Stanford there. And so there were some of the students from Berkeley, and then, of course, many new students at Stanford, because the logic group there had expanded very, very much. Also, when Myhill was there, he was quite influential in getting people to come there. And so I then, of course, there were very interesting students who worked with me then at Stanford after I moved there.
Yes, you have some very famous students there. It would take a long time to go through all the students and everything they did. Actually, you mentioned Pat Supes, if I could move to Pat Supes, because you had a really long association with him, dating back to your first period at Berkeley, a long time before that. You have a famous joint 1958 paper, Foundational Aspects of Theories of Measurement, and that puzzled me a little bit in a sense because it contributes to mathematical psychology. So it's not exactly logic. So I'm just curious about your association with.
Well, it was really concerned with a certain kind of model theory. I mean, that was really influence of Supes. I've been retained very close friendship with him over the years. I mean, he was just a beginner at Stanford when Montague and I took his course at Berkeley in the mid-50s. But I kept in close contact with him, and he very often was able to give me a summer job at Stanford working in his research group there. And so we had been very close over the years. Now, he was interested in mathematical psychology and the question about uh, uh, logical deductions. How could logic be applied to questions that might have some psychological interest? And so measurement or understanding relations between different theories of measurement or different scales of measurement or how to connect those things was something that had been much of a concern to him. And so that was how our joint paper arose in talking about, in particular, questions about relating measurement also to probability theory. And so it was his influence, and I made some contributions, so to speak, really on the side of model theory, not on the side of applications to psychology.
Does that connect with your later interest in logic of probability, the work you did with Krauss?
Well, that really, no, that really came up from, well, of course, probability is a very important area, and the connection with logic, I mean, is there from the very beginning of the subject. But what inspired that work with Peter Krauss, who was a student at Berkeley, and then he finished up with me after I was at Stanford, really came from the paper. Now I'm going to block on names. Chaim Geifman, who's been for many years, he was from Israel, but for many years he's been a professor at Columbia. Chaim Geifman had a paper about assigning probabilities to logical formulae. In other words, the logical formulae form a Boolean algebra, and you can think of having a probability measure on that Boolean algebra. And so he had some interesting results. So that was really the inspiration for the work with Peter Krauss, which resulted in his thesis and our joint paper. Was expanding on from the original work of Geifman.
Oh, I need to read it, I think. So jumping around a bit, going back to an earlier theme of the origin of computer science departments, you were also present at the early days of computer science at Stanford. George Forsyth, Donald Knuth, and John McCarthy were all there, well-known people. As less known fact was that more briefly, Barbara Liskov, another Turing Award winner, was there. Okay. Do you have any remembrances from those days?
Very much, yes. Well, you see, Forsyth had always been there. He was in Mass, and there were other people in Mass in numerical analysis, and they were beginning to feel that it was time that computer science had some independence. And really, the mathematics department at Stanford, which was very heavily oriented toward classical applied mathematics, was very happy to give away numerical analysis and other things to form the new department. I wasn't involved in the formation of the new department, but I knew everybody was there. Very soon, Don Knuth moved over from Caltech to Stanford, and John McCarthy came and started up his AI Institute, and I knew many people involved in that. And of course, I had known McCarthy before uh, from the time that he and Minsky, so to speak, started their approach to AI in the 50s. So I was very much a colleague of very, very many people there, though I wasn't directly involved in the computer science department. However, from the point of view of logic and automata theory, I gave some courses. Barbara Litzkoff was in one of my courses. It turned out to be a very lively group. There was lots of interest from many different students there. And so I remember her very fondly from there because she was such a bright light, and of course is continued to be a major figure now in computer science. So that was where I first had any connections with her. That seminar I gave at Stanford in the 60s.
Wow. So did you know McCarthy and Minsky already? Like, was that when you were in Princeton earlier? Is that how you got to know them?
Uh, yeah, I didn't know McCarthy all that very well, but I got to know Minsky very well. Minsky had very interesting idea about register machines, and I proved some small results about that. And over the years, I had a very, very close connection with Marvin Minsky and visited him many times in Cambridge, Massachusetts, there. And so that friendship, yes, went back to the late 1950s.
And so did that lead to your work, or I guess it would connect to your work with Bill Rounds on automata theory, which is also done in the Stanford period?
Well, I think it was really just. I think it was really just the general development of automata theory, not particularly Minsky, though of course he's a major figure, uh, and of course Rabin had gone on to do many very fundamental things, not only probabilistic automata but also uh, automata on infinite trees. And so we were quite inspired by those developments. And so that's how uh, uh, I had two students in automata theory there that finished up while I was at Stanford.
Right. Okay, so jumping back to logic and set theory. So a major thing that happened in this period was that Cohen, who's also at Stanford, introduced forcing to show the negation of Cantor's continuum hypothesis was consistent with set theory, and thereby with Gödel's result showing that it was independent of set theory, which was a major result. Later, you and others showed how this could also be done using Boolean valued models, and you were awarded the Leroy P. Steele Prize for that in 1972. So that's a huge development and a huge story. Can you tell us something about that period and those times?
Cohen came from Chicago, and there were many people in Chicago, including Myhill and Narode, and of course, Saunders MacLean was a very major professor there. His original thesis was in logic from Göttingen. At the time that he got his PhD, very often people went to Germany to get a PhD rather than get a PhD in the United States. And so he was one of the late people who had his uh, his graduate work in that way. However, uh, uh, Saunders MacLean very soon transferred over to topology, algebraic topology, and of course was very intimately involved with many major figures there. Paul Cohen was a very, very brilliant student and at Chicago and did major things in classical analysis, but he heard a lot about logic and was always rather irritated by the logicians because he felt that they claimed too much importance. He really looked down very much upon it, and he kept hearing about how there was the proof of the consistency of arithmetic uh, uh, done by proof theory in logic. He heard that from many people. Stanley Tenenbaum knew Cohen very well while he was working in Chicago. And so when Cohen came to Stanford, there was a lot of logic going on there. Supes, of course, in philosophy, Pfefferman in mathematics, and Kreisel loomed very large and was very much in view there. And so Cohen especially liked to be able to do things on his own. For example, he proved Tarski's decision method for real closed field his own way. I don't think he ever read any of the Tarski papers. He just did his own version himself. And he said, I'm going to show the consistency of arithmetic. And so he really reinvented for himself, completely on his own, the method of showing consistency of first order arithmetic. And now he said, I'm going to show the consistency of second order arithmetic. And so in thinking of second order arithmetic, he had to consider quantifying, in effect, quantifying over infinite sets or over functions. And so he had to think in terms of approximating functions a little bit at a time and giving some kind of relationship to force a function to have some properties just on the basis of a small amount of information. And so after he started getting that idea of forcing properties based on information, he then saw that he could extend that to not just to functions over the integers, but to the transfinite realm as well. And so that's how he invented force. And of course, he was quite influenced by Gödel's work. He knew, of course, about constructible sets. And in the beginning, you can understand it coming from the thinking about the arithmetic. He made very strong use of taking countable standard models of set theory. I mean, by the Leeuwenheim-Skolem theorem, even a transfinite model has a first order equivalent countable submodel. And so he used countable standard models in connection with his forcing. And of course, everyone was completely amazed by what he was doing. He was rather bitter at times that people criticized his work. Several people were afraid that he was making a mistake, and with his claims of showing the consistency of the independence of the continuum hypothesis, that he might have made a mistake, and they raised various questions there. But of course, in the end, it turned out he hadn't made any mistake, but he was very annoyed by anyone ever questioning that he might be wrong about things. So all kinds of people were very interested in this. Bob Solovey had come after his PhD in Chicago, where of course he knew about Cohen and many other people, had come as a junior professor to Berkeley, and he was very, very interested in the Cohen developments. And so he came to Stanford many times, and we had many sessions with Cohen, with Pfefferman, Kreisel, Solovey, other people too, trying to understand Cohen's work. And so one day, Bob Solovey said, I've been thinking about the notion of forcing, and you can reinterpret what Cohen has been doing by saying he associates a Boolean value by looking at the forcing conditions that force a sentence to be true. You could make those forcing conditions into an element in a Boolean algebra. And so he said he's giving Boolean values, these forcing notions are giving Boolean values to statements about set theory. Now, this was just about when he brought that up and explained how he connected that point of view with the techniques of forcing, was just about the New Year's break. My wife and I were living in San Francisco at that time, and when I went home over the holiday, I thought, wait, if Cohen via Solovey can give Boolean values to formulas, why don't I start with the Boolean algebra in the first place, which could be easily described, and think in terms of giving Boolean values to using a Boolean algebra, a given Boolean algebra. Instead of doing Cohen forcing, you pick the right Boolean algebra, and then you extend the Boolean algebra from being just a model of propositional calculus to being a model of not only first order logic, but higher order logic by thinking of the power set operation, which generates the sets in set theory, is just iterating two-valued combinations using two-valued logic. Why not use Boolean valued logics to iterate things into the transfinite? And so that was how I saw an insight into starting with Boolean algebras first and then using that to interpret set theory, and of course, referring to, of course, the kinds of things that Cohen did. In any case, it redoes his theorems in a different way for the independence of the continuum hypothesis. The way it comes about, of course, is that Boolean values, multi-valued logic can give you many more sets of integers than you had before. Instead of taking just two-valued sets of integers, you can, if you take multi-valued sets of integers, you can have an awful lot of them, and that's how you get connected up with cardinal numbers. Of course, there are a lot of details to work out that way. Of course, Cohen, I don't mean Cohen, I mean Solovey immediately said, wait, I thought of that myself. And so when it came time for the UCLA Set Theory Institute a couple of years later, we decided to make it a joint paper on Boolean valued models there because really the motivation came from Solovey, and Solovey had really many insights there. And so I was really auxiliary to the development with Solovey. So that's how it came about.
Oh, that's a really interesting story. Thank you. Yeah, I know that I was supposed to ask you about the UCLA Set Theory Institute because that was an important meeting, but is there anything else you'd like to say about that? Or is it just simply the importance of being able to present the Boolean valued models there that was important to you?
Well, it was the first time that all kinds of people came together. There was amazing interest in set theory and models of set theory. And so it came at a very fortunate time that all kinds of people could get together to discuss these things. One anecdote I'll tell about it is that Saul Kripke was going to be one of the featured speakers at UCLA at the big set theory meeting. And he was very late in arriving. I was one of the organizers on the organizing committee. And we got this telephone call, and it was Saul Kripke said, "I'm at the airport, but I don't have any money." I said, Saul, it doesn't matter. The meeting is about to start. You've got to get here. I'll meet you at the curb and I'll pay the taxi. Don't worry about it. So Saul Kripke arrived and I picked up his bags and said, Saul, we have to hurry to get you registered for this. It's the last minute. And so walking through the hallways to get to the registration room, we passed Jerry Kiesler. And Jerry Kiesler said, "Hi, Saul. I see you got someone to carry your suitcases." Saul Kripke was always has been amazing to get people to help him to do many things in life. And so that's one of my favorite stories about him, that I was carrying his suitcases.
Oh.
But I just want to say something as the aftermath of the set theory conference. It was a very, very big conference, and the publication of the proceedings of it was quite complicated. I'm afraid I slowed up the publication very much. It was finally published in 2 volumes, but the Scott Solovay paper never appeared in the proceedings, even though we gave several lectures during the time of the actual conference. The reason was when it came time to make the final paper, this was in 68, 69, when I was on sabbatical in Amsterdam, Solovay came to visit me, but by this time, dozens and dozens of people had proved so many important things about set theory, independence results in set theory of all kinds. Solovay wanted to make sure that everything was incorporated into the paper, and I'm sorry to say it was too much for me. I couldn't really synthesize all the things that Solovay wanted to put into the paper, and so I could never make the final version of it. Fortunately, from the notes that we had prepared for UCLA, fairly soon after that, John Bell wrote a very good book, starting with our lecture notes, wrote a very good book on Boolean valued models for set theory that, in effect, is the Scott Solovay paper, but done by another party that way, and is very helpful because it carried out things in the spirit that we had wanted to have it done, and is available now for students if you want to look at that point of view.
Well, thank you. So you did many different things, so the interview jumps around a little bit, but you mentioned Saul Kripke, so that made me think of tense logic and modal logic. And there was lots of people around in Stanford. There's a big interest of yours on famous people like Arthur Pryor on tense logic, Jaakko Hintikka, John Lemon, Richard Montague, who we already came across. Can you tell me something of that area and developments in that area, your interactions there?
Well, I'd already learned about modal logic as an undergraduate, and Tarski and collaborators of his had also papers on modeling modal logic that I knew. But then with my friendship with Richard Montague at Berkeley as an undergraduate, he was very interested in what you might call today philosophical logic. That is very ways of thinking of logical methods to analysis of philosophical problems or questions about language. And so that's my introduction to modal logic came that way. So by the time of the mid 60s, there were lots and lots of people in philosophy. Uh, you mentioned Hintika was a very strong one. Uh, Kripke had started as a teenager being interested in modal logic and invented Kripke models for modal logic, which turned out to be also in another form already invented by Tarski in the much earlier papers there, but people in philosophy didn't. Tarski's formulations were very much done in terms of algebras of operators on Boolean algebras. And so Kripke's approach with Kripke structures was much easier to understand for many people. And so, as I say, he invented that when he was a teenager and started his career from that point of view. And of course, many people, Hintika, pursued it very, very strongly in many different directions. And so questions about tense logic could be reformulated in terms of Kripke models, as many people saw. So there was a lot of that in the air, and there were many visitors who came to Stanford to do that. I don't remember how I first met John Lemon. He was working in Southern California, but he was a very congenial person and gave interesting lectures. And so I struck up a relationship with him, and that we wanted to do some more of a textbook on modal logic using his work, but also using things from the Boolean algebra side as well. And so we had started to make that development. And Christer Segerberg was a PhD student of mine in Stanford at that time. And so we had some notes that we put together, but alas, John Lemon had a weak heart. And one time he was on an outing to mountains near where he worked in Southern California for a picnic with people, and he just had a heart attack and died suddenly on this outing. So that was terribly sad. It was terribly sad for him because he influenced so many people and students and colleagues. So I never finished trying to write the Scott Lemon textbook, but an abbreviated version of it was put together by Christer Segerberg, which was published. So that's my connection with John Lemon.
Yeah, I enjoyed reading that book many years ago. I still remember it. Yeah. So actually, there's a connection with computer science, which is that Amir Pinelli, another Turing Award winner, won the 1996 Turing Prize. And the citation begins, I read, for seminal work introducing temporal logic into computing science. And it is part of a very long and practical development. Did you have any hint of those things in those days?
No, I didn't really. No, that was a different point of view. Of course, with all of those things, people want to take over things from logic, and so tense logic can be useful there. But of course, those kind of developments are much more concerned with particular applications, like proving properties of programs in terms of when time may be an essential thing I mean, there are many questions about time in the execution of programs, and so that's much more concerned with the implementation of computations on computers.
Yeah, there's so many connections, which makes things interesting. Well, jumping back to logic, there's infinity logic, yes, another variety of logic. That was important to you, and you worked on that with the Scott sentence and so on. Can you say a little about that interest of yours?
Well, that really came earlier. I mean, Tarski had, and various people, certainly Russians and others, had worked very much on infinitary logic, Tarski and his students. And so I learned about that at the time at Berkeley, both as an undergraduate and later as when I was there as a faculty member. And so already at the Cornell conference, Tarski and I had a joint paper on infinitary logic, and so that was where my interest came from there, the developments from that. And so I think the things that you referred to are things that I did in the early 60s in Berkeley later on, but the original influence came from Tarski's earlier work on infinitary logic.
Oh, okay, another Tarski point. He features often. Well, this is going to be Tarski again, perhaps. So introduces to constructive logic was another topic of importance to you this period. And there are links to Tarski and the areas of great interest for questions of the foundations of mathematics. What was the abiding fascination for you in this area, which continued, maybe still continues?
Well, in connection with modeling of modal logic, Gödel had already pointed out that there was a connection between modal logic and intuitionistic logic. And Tarski had introduced the topological models for modal logic, which include topological models for intuitionistic logic. I mean, roughly speaking there, if you think of a topological space, then the subsets of the space form a Boolean algebra. But if you take the interior operation, then the open subsets of the topological space form not a Boolean algebra, but form a certain kind of distributive lattice. And Tarski realized very early on that the open sets form a model for hiding algebras or intuitionistic logic. And of course, that's also connected very closely with what happens with Kripke models and things like that, too. There are many connections there that people developed over the years. So I knew about that work from the early days with Tarski and connections between Boolean algebras and algebras with operators modal logic. But I really didn't get into understanding constructive reasoning until later. Of course, it was very strongly emphasized in the important textbook by Steve Claney, Introduction to Mathematics, and both from the point of view of proof theory and from the point of view of realizability interpretations of intuitionistic logic. And so when I came to Princeton and was very much then influenced by Kreisel, I really looked much more into the questions of intuitionistic logic from that point of view. Though I never became adept at doing things in proof theory, I certainly understood recursive function theory and realizability interpretations. And so that was my connection. And of course, I met various people connected with intuitionistic logic that way. And so that was really how I had my strongest interest in it, was from that point. Tarski never taught about proof theory at Berkeley. Pfefferman, who was later very strongly influenced by Kreisel and his interests, really was the first of Tarski's students, I think, who really went back and read Hilbert Bernays and those kind of things, and then made major contributions to proof theory. But I didn't develop along those lines at all, even though I did understand quite a bit about constructive logic in the way that I just indicated.
Yeah, well, thank you. So there's all these connections between Boolean algebra and topological models. So, and continuing to jump around a little bit. So Boolean valued models came up again for you another time, but in yet another context of non-standard analysis. So I'm very curious about that, whatever you have to say.
Well, if you look at ultra products, you can really think of ultra product as starting with a Boolean valued model and then taking homomorphism, so to speak, by using a filter on it. And so you could really start with Boolean valued logic and then look at trying to cut down the Boolean values by means of a filter. And so those connections, and of course, as Abraham Robinson emphasized so strongly, he thought of getting his models for non-standard analysis by using ultra products to get to the infinitesimals. And so so there was lots of connections there that brought the Boolean valued models and non-standard analysis together. But on the other side, going back to Tarski's topological interpretation of intuitionistic logic, after the period of development of Boolean valued models in set theory, it occurred to me that using the lattice of open subsets, instead of using a lattice as a complete Boolean algebra to make a Boolean valued models in classical logic, you could use the lattice of open subsets to make up models of intuitionistic analysis. And so I did that. I thought of that after the after the period of the development of Boolean valued models. That's how I thought of doing modeling intuitionistic analysis using the topological interpretation.
Right, thank you. We'd have to cover the Amsterdam and De Backer and so forth. Is that okay? We've got a few minutes.
Yes.
Okay.
So I was at Stanford for about 6 years, and we've covered some of the developments of there. And of course, it was very lucky. There were many excellent students there, both for Pfefferman and myself, and many visitors came to Stanford. It was a very, very active time. And so I was then eligible for a sabbatical in 68, 69. And I'd already met, at various conferences and other places, many people from the Netherlands. And so I decided it would be very nice to have a sabbatical in Amsterdam. So I knew Anna Troelstra, Dirk van Dalen. I'd met Heiting. Heiting was just retired from his chair. And so the University of Amsterdam had money that they could have for a temporary visitor there. And so I agreed to come to Amsterdam, where I could also do some teaching there. That was also, I must have met Esker Dijkstra during those things, but very strongly was in the computer science there in Amsterdam was Ad van Wijngaarden, who was a very big mover, especially in development of algol and eventually in algol 68, which was apparently enormous effort on his part and a lot of battles with other people who had many different ideas about how algol should develop. But algol 68 finally was Van Wijngaarden's baby, and I got to know him and made friends with them. One of his students was Jaco de Bakker. There were others there too that I had a lot of connections with. And de Bakker and I had very many interesting times together. And so then in the summer of 69 was when I wrote up the notes for the work that de Bakker and I had done. And so that all developed during that sabbatical year, 68, 69. The summer, of course, was very, very important for me because that was when on the idea of Pat Supes that I could come to the IFIP Working Group 2.2, where he was a member, but he couldn't attend it that year. That was where I met Strachey and heard many, many things, questions about language design and all the arguments that were going on, especially with the development of algol at that time. And so after hearing all of those things and seeing the approach that Strachey wanted to take, I felt very, very much attracted to that point of view of thinking of computer languages. To backtrack a little bit, one thing that happened in Amsterdam is Donald Davidson, the philosopher, had been a long-term professor at Stanford, but in 68, he left Stanford to go to Princeton. And so he was at Princeton, and at the end of that academic year, he was on a trip to Europe, and he came by in Amsterdam. And so he recruited me to come to Princeton. He was directly responsible for me after my sabbatical, leaving Stanford and going to Princeton. One of the things that was difficult in Stanford was that the mathematics department was very, very oriented toward classical analysis and was not really interested in helping with the development of logic. And I was kind of split between mathematics and philosophy, but I felt in mathematics that logic was not especially welcome there. And so that's how Donald Davidson influenced me to come to Princeton. Of course, I knew Princeton as having been a graduate student there, but that's how I got to the philosophy department in Princeton as a faculty member. However, having met Strachey and became so involved in thinking about the development of computer languages from those connections, I made a special plea that I could have my first semester on leave from Princeton so I could visit Oxford in order to do work with Strachey, and they reluctantly agreed to that. And that was That was how I went to Oxford then to work to continue work with Strachey. So the next time we meet, Gordon will pick up the story there with the time in summer of '69 and starting then coming to Oxford and working with Strachey. So we'll pick up the story there.
We will. Thank you.